In this video, we start part 2 of our chapter 3, which is about the simplex method. In the second part of the chapter, we're going to see these topics. In this video, we will discuss cycling, and we will see how we can make the simplex method avoid cycling. Next, in section 3.5, we will understand how the simplex method is able to find an initial basic feasible solution. In section 3.6, we will see a different geometric interpretation of the simplex method. In particular, this geometric interpretation will allow us to understand why this algorithm is called the simplex method. Finally, in section 3.7, we discuss the running time of the simplex method. So far, in fact, we have only discussed the running time of a single iteration. This video is fully devoted to section 3.4, and we're gonna see that the simplex method can cycle, and we will see how to avoid it with the lexicographic pivoting rule and blends rule. The first thing that I want to convince you of is that the simplex method indeed can cycle. In our example, we will start with the simplex tableau that we have in this slide. In particular, I will show to you that the simplex method can cycle even with the following very specific and reasonable pivoting rule. In a pivoting rule, first I have to tell you who enters the basis in case I have several negative reduced costs. Here I'm going to select the non-basic variable with the most negative reduced cost. I also need to specify to you who leaves the basis in case several basic variables go to 0 in the new basic feasible solution. In this pivoting rule, I will be selecting the one with the smallest subscript to leave the basis. So then let's start our sequence of tableaux. Once again, this is the tableau that we have just seen, and it is our initial tableau. As you can see, the basic variables are x5, x6 and x7, and the cost of the corresponding basic feasible solution is -3. In this tableau, I have two negative reduced costs, -3/4 and -1/2. The most negative is -3/4, so x1 enters the basis. I compute the two ratios 0 divided by 1/4 and 0 divided by 1/2. The smallest among the two is of course 0, so we have a tie, and the tie is resolved by picking the smallest subscript, so I will have x5 leave the basis. So I have now selected my pivot column and my pivot row, and I can perform my first pivot. If you now perform the elementary row operations that transform the first column of the tableau into the first unit vector, you obtain the tableau below. Again, I have two negative reduced costs, -4 and -7 divided by 2. The smallest is -4, so x2 enters the basis. The ratios that I need to compute to determine theta star are 0 and 0. I have a tie between x6 and x7, and so I pick x6 to leave the basis. If you perform the corresponding elementary row operations, you obtain the tableau above. Now I have only one reduced cost, so x3 will enter the basis. The smallest ratios are now given by x1 and x7 because they're both zeros, and the tie is broken by having x1 leave the basis. If you perform the elementary row operations, you obtain the tableau below. Now I have two negative reduced costs, -3 and -2, so I will have x4 enter the basis, because -3 is the smallest of the two. When I compute the ratios to determine theta star, the smallest ratio is 0, which is given by x2, so I will have x2 leave the basis. Next, I obtain the tableau above. Also here, I have two negative reduced costs, -1 is the smallest, so I have x5 enter the basis. I have two ratios that are 0 that determine theta star, and this corresponds to x3 and x4, therefore I will have x3 leave the basis. Next, I obtain the tableau below. In this tableau, I have two negative reduced costs, -2 is the smallest one, so x6 enters the basis. Then I only have one ratio that is equal to 0, and so it determines theta star, and this is the one corresponding to x4. So I will have x4 leave the basis. And the next tableau is the one above. Now, if this tableau looks familiar, it's because, in fact, it coincides with the very first tableau we started from. Therefore, after 6 pivots, we have the same basis and the same tableau that we started with. This means that we never moved in any of these iterations. Therefore, theta star was equal to 0 in each iteration, and in fact that's what happened. And you can also check that in each tableau we had the same feasible solution and the same cost. In particular, the 3 here never changed, so the cost was always minus 3. This means that the simplex algorithm with this pivot rule will keep cycling forever. In fact, if we continue with the simplex algorithm from this tableau, in 6 more pivots, we will obtain once again the same tableau, and this cycle will repeat forever, so the simplex method will never terminate. Now, this example shows that using this pivot rule, the simplex method may cycle. Fortunately, this doesn't happen for every pivoting rule. And in the rest of the video, we will see 2 specific pivoting rules that guarantee that the simplex method never cycles. These are called anticycling rules. In particular, using these anticycling rules, we will obtain that the simplex method will always terminate, and this will allow us to extend the theorem 3.3 to degenerate problems. In particular, this will imply that if the optimal cost of a linear programming problem is finite, then there always exists an optimal basis. And remember that an optimal basis is defined as a basis capital B satisfying B inverse B greater than or equal to 0 and reduced costs greater than or equal to 0. Let's start with the lexicographic pivoting rule. This is the first of the 2 pivoting rules that we will see that always avoid cycling. To introduce this pivoting rule, we need to define first what it means for a vector to be lexicographically larger or smaller than another vector. Given 2 vectors, u and v, we say that u is lexicographically larger than v, and we write it like this: whenever u and v are different, and the first component that is different in u and v is larger in u. Let's immediately see an example over here. The vector on the left is lexicographically larger than the one on the right, and we can check that by looking one by one all the components. In the first component, both these vectors are zeros, so we have a tie here. So we need to look at the next component. The second component is 2 for both of them, so we need to look at the third component. The third component is 3 in the vector on the left and 1 in the vector on the right. Therefore, the vector on the left is the one that is lexicographically larger. Note that at this point I don't care what's going on in the next components. So in particular, the fact that the last component is larger in the vector on the right has no implication for our definition of being lexicographically larger. Vice versa, of course, we say that u is lexicographically smaller than v if the first different component is smaller in u. In our second example here, we have that the vector on the left is lexicographically smaller than the one on the right, because already the first component is smaller in the vector on the left. Sometimes we will also say that the vector u is lexicographically positive, and this means that the vector u is lexicographically larger than the vector containing all zeros. In other words, it means that u is different from 0 and the first non-zero entry of u is positive. We're now ready to define the lexicographic pivoting rule. Like in any pivoting rule, we need to explain how to break ties for the variable that enters the basis and then for the variable that exits the basis. Let's start to see who enters the basis. One of the great advantages of the lexicographic pivoting rule is that there is no restriction at all. In fact, you can choose an entering column aj arbitrarily, as long, of course, as its reduced cost c bar j is negative. Accordingly, the vector u will be the jth column of the tableau. Now let's see how we can understand which variable should leave the basis under the lexicographic pivoting rule. For every I with a ui positive, we divide the ith row of the tableau by ui and we choose the lexicographically smallest row. Such row will be our pivot row. Note that this is in a sense an extension of what we were already doing to determine theta star. In fact, earlier on, to decide theta star, we were already considering all the i's with ui positive. But instead of dividing the all ith row of the tableau by ui, we were only dividing the entry of the ith row in the zeroth column by ui. Essentially, the lexicographic pivoting rule is telling us that in case we have a tie among 2 of these ratios, you need to divide also the entries in the first column by ui and pick the smallest. If you have again a tie, you look at the second column of the tableau and so on and so forth. To clarify our minds, let's see immediately an example. In this example, we're omitting the 0th row, we don't really need it. Let's say we've already picked the pivot column, and it is the one highlighted here. To obtain our theta star, we were looking at the positive entries in the pivot column, in this case 3 and 9, and then we were looking at the ratios 1 divided by 3 and 3 divided by 9. In this case, we have a tie, and so we look at our pivoting rule. What it tells us is that in order to break this tie, we should now compute the ratios 0 divided by 3 and 0 divided by 9. So essentially, we should look at the first column of the tableau instead of the 0th column. But in this case, you see, we still have a tie because we have 0 in both cases. So now we look at the second column, 5 divided by 3 and 7 divided by 9. The smallest is 7 divided by 9, therefore we pick the third basic variable to leave the basis, so the pivot row will be the third and the pivot element will be 9. Equivalently, you could have followed word by word our pivoting rule, and you could have immediately divided the full first row by 3 and the full third row by 9. And then the tie between the first and third row is resolved by performing a lexicographic comparison of these two row vectors. The two vectors coincide in the two entries but differ in the third, and since 7 divided by 9 is the smallest, then the third basic variable exits the basis. Now, in order for this lexicographic pivoting rule to be actually a pivoting rule, it should always uniquely identify the exiting variable. And if you think about the rule, this is not obvious. In fact, it can happen that by dividing these rows that define theta star, so among which there is a tie, you obtain identical rows. And in this case, the lexicographic pivoting rule doesn't tell you which one to choose. The great thing is that this can never happen, which implies that the lexicographic pivoting rule always leads to a unique choice for the exiting variable. Why is that the case? To show this, we will use once again the fact that our matrix A has linearly independent rows. Let's prove this by contradiction. If the lexicographic pivoting rule doesn't lead to a unique choice for the exiting variable, it means that there are at least two rows that are proportional to each other. But now remember that the rows of the simplex tableau, if you delete the 0th column, are two rows of the matrix B inverse A. So we obtain that there are two rows of the matrix B inverse A that are proportional. In particular, this means that the matrix B inverse A has rank smaller than M. Since B inverse is of course invertible, we obtain that also the matrix A has rank less than M, and so it doesn't have linearly independent rows. So we obtain a contradiction, and this is how we conclude this proof. We are now ready to show that the lexicographic pivoting rule always avoids cycling. Here is a statement. In the first lines of this statement, we have an assumption that could seem strange at first sight. We will see later that this is not problematic at all. So let's read through the statement. Suppose that the simplex algorithm starts with all the rows in the simplex tableau, except for the 0th row, lexicographically positive. If the lexicographic pivoting rule is followed, then A. Every row of the tableau except the 0th row remains lexicographically positive throughout the algorithm. B. The 0th row strictly increases lexicographically at each iteration. And finally C. The simplex method terminates after a finite number of iterations. Note that in this statement we're not really interested in A and B so much, we really are just interested in C. However, in order to prove C, it will be useful to first prove A and B. Before we start with the proof, I want to state here few simple properties of the operator being lexicographically larger. All these properties are very intuitive, but I recommend that you prove all of them. They're actually really simple to show. The first property here tells us that U is lexicographically larger than V if and only if U minus V is lexicographically larger than 0. In the second property here, we have that if a vector U is lexicographically positive and we have a positive scalar alpha, then the vector alpha U is also lexicographically positive. In the next property, we have that if we have two lexicographically positive vectors, then also their sum is lexicographically positive. In our last property, we have that for any vector v, if we sum v with a lexicographically positive vector, we obtain a vector that is lexicographically larger than the original vector. Let's now see a sketch of the proof of theorem 3.4. I will leave you as an exercise to write down a complete proof of this theorem. First, let's prove A. We want to show that every row of the tableau, except for the 0th row, remains lexicographically positive throughout the algorithm. As always, we denote by xj the variable that enters the basis, and the lth row is the pivot row. From the definition of L, we have that UL is positive. Since our lexicographic pivoting rule chooses the row L, it means that the lth row of the tableau divided by UL is lexicographically smaller than any other row I of the tableau divided by UI, provided that UI is strictly positive. Now let's see how the rows of the tableau look like after the elementary row operations are performed. First, we're going to consider the new lth row. This is the simplest because it simply is the old lth row divided by UL. This is how we make the pivot element equal to 1. Now the old lth row is lexicographically positive and the UL is positive. Therefore, the new lth row will be lexicographically positive. Now we have to consider all the remaining rows of the tableau. So let's look at row I for I different from L. After the elementary row operations, the new ith row will be equal to the old ith row minus UI over UL times the old lth row. Now we're going to consider separately two cases depending on the sign of UI. First, we consider the case where UI is less than or equal to 0. Since UL is positive, we have that minus UI over UL is greater than or equal to 0. Therefore, the new ith row is the sum of two lexicographically positive rows, namely the old ith row and minus UI over UL times the old lth row. Therefore, the new ith row is lexicographically positive. The remaining case is when UI is strictly positive. In this case, we can obtain that the new ith row is lexicographically positive using our relation over here. In fact, everything you need to do is to bring the left hand to the right and then multiply by UI. You will obtain that the old ith row minus UI over L, the old lth row, is lexicographically positive. Therefore, the new ith row is lexicographically positive. And this completes the proof of point A in the theorem. So now let's look at point B. In B, we need to show that the 0th row strictly increases lexicographically at each iteration. Note that at the beginning of an iteration, the pivot element is positive and the reduced cost in the pivot column is negative. Now we want to understand what happens to the 0th row after we perform the elementary row operations that transform the reduced cost in a 0. Since the reduced cost is negative and the pivot element is positive, to obtain a 0 we need to add a positive multiple of the pivot row. But now the pivot row is lexicographically positive, and so the 0th row will increase lexicographically. We have therefore shown the point B. Let's finally prove point C. Now the 0th row, like all the rest of the tableau, is completely determined by the current basis. Furthermore, we have just shown that the 0th row strictly increases lexicographically at every iteration, and this directly implies that no basis can be repeated twice. If no basis can be repeated twice, we cannot have any cycling, and so, since there's a finite number of bases, the simplex method will terminate in a finite number of iterations. This concludes the proof of point C and of the whole theorem. A big advantage of the lexicographic pivoting rule is that it can be used very easily together with the full tableau implementation. This is clear from the definition of the lexicographic pivoting rule, since it involves dividing some rows of our tableau. A natural question is then if the lexicographic pivoting rule can also be used for the revised simplex method. And in fact it can. It's a very good exercise for you to define a lexicographic pivoting rule designed explicitly for the revised simplex method. Essentially, you will see that instead of considering the rows of the tableau, you will have to look at the rows of the inverse basis matrix B inverse. So in particular, you will need to form this inverse matrix explicitly. The last thing that I want to say about the lexicographic pivoting rule is about the strange assumption that we had at the very beginning of our theorem 3.4. In fact, if you remember, in order for the theorem to hold, we need to have an initial tableau with lexicographically positive rows. In general, of course, you don't have such a property. Now, if the basic feasible solution you start from is non-degenerate, then this assumption is always satisfied, because in the 0th column you have all positive entries. However, if you have a degenerate basic feasible solution, then you have a 0 in the 0th column, and the next non-zero entry could be very well negative. However, we can slightly modify our initial tableau in order to satisfy this assumption. The idea is to use the fact that the columns corresponding to the basic variables are unit vectors. So what we can do is rename all the variables so that the basic variables are the first m ones. Then in our tableau, the first m columns will be the m unit vectors. This implies that except for the 0th column, in every row, the first non-zero entry will be a 1. Therefore, all the rows will be lexicographically positive, as required. So we have shown that no matter how our initial tableau looks like, we can always transform it in an equivalent one that satisfies the assumptions of our theorem 3.4. The next pivoting rule that we're going to discuss is Blend's rule, which is also known as the smallest subscript pivoting rule. This rule is very simple to define, so let's do it right away. Regarding the entering variable, we need to find the smallest j for which the reduced cost c bar j is negative and have the column aj enter the basis. Regarding the exiting variable, out of all the variables xi that are tied in the test for choosing an exiting variable, we select the one with the smallest I. Essentially, in this pivoting rule, when we have a tie, we always break it by picking the smallest index. It's very important here that you don't get confused between the indices of the x variables and the number of the basic variable. In this pivoting rule, we always select the variable xi with the smallest I, and this is different from selecting the variable xbh with the smallest h. So be careful about this. Note that while the lexicographic pivoting rule, as we have defined it, is tailored only for the full Tableau implementation, Blend's rule can be directly used in all the implementations we've seen. In particular, it can also be used in the revised simplex method, in which the reduced costs of the non-basic variables are computed one at a time, in the natural order, until a negative one is discovered. And if you remember, this is the implementation that we discussed when we saw that the revised simplex method in the average case is better than the full tableau. Also, Blend's rule, like the lexicographic pivoting rule, avoids cycling, and so it implies that using this rule, the simplex method terminates after a finite number of iterations. This is formally stated in this theorem. If the simplex method uses Blend's rule, it terminates after a finite number of iterations. We're now going to show this theorem. We're going to prove this theorem by contradiction. So assume, for a contradiction, that there exist basis matrices let's say B0, B1, and so on and so forth until Bk, and then again B0, that form a cycle. This proof is based on the concept of a Flickle variable. We say that an index is fickle if it is a basic index in some bases, but not in all the bases of the cycle. So if it is a basic index in some, but not all bases in the cycle. The first thing to observe is that if a variable I is fickle, then the corresponding variable xi will be equal to 0 in the solution corresponding to this basis, since the solution x remains the same throughout the cycle, I fickle implies xi equal to 0 throughout the cycle. The analysis in this proof will follow from the analysis of the largest fickle index. Let's call it T. So let T be the largest fickle index. In most of the proof, we will analyze two specific change of basis. First, we analyze when T exits the basis, and then we analyze when T enters the basis. Since T is fickle, both these change of basis exist. So let's start with, let's say, A. There exists B in the cycle such that T is in B, and I'm going to use this notation meaning that T is a basic index for B. So meaning T is a basic index for B. So and T exits the basis. Therefore, T will not be in the next basis in the cycle. Let's denote by S the index that enters the basis. Let S be the index that enters the basis. So S was not in B and it will be in the next basis, and this implies that S is fickle as well. Since T is the largest fickle variable, we have that S is strictly smaller than T. Let's denote by bar C the vector of reduced costs and by D the basic direction. Next, we're gonna write down a table that I will fill in throughout this proof. So first, I'm gonna divide a different type of indices. So index type, I will have T, and let me just remind you here that this is the one that exits the basis. Then I have the variable S, which enters the basis. Then I break down the remaining indices as follows. So I look at the basic indices, different from T, since I've already written T above, and with I fickle. Then I look at the indices I in the basis with I not fickle. And finally, I look at the indices that are not in the basis. And since I already consider S separately, I different from S. Now, for all these types of indices, I want to consider the corresponding components of C bar and D. And later on, I will consider even more vectors. Let's start with C bar and see what we can say. We know that the reduced costs of all the variables that are in the basis is 0. So in particular for T, this is equal to 0 because it is in the basis. And then for also all the other ones, in the basis, this is just equal to 0. What about the component of C bar corresponding to S? Well, since S enters the basis, we know that the reduced cost is strictly negative. And then the final type of component, I don't really care. So I'm just going to leave here a question mark. I'm not going to need it later. Next, let's discuss the direction vector d. Since t is chosen to exit the basis, we know that the component dt is strictly negative. And since S enters the basis, this is the component equal to 1. Then all the other non-basic components are equal to 0. Then for the basic variables which are not fickle, I don't care, so I'm just going to put a question mark because we're not going to need it later. Now I want to show you how you can fill in the remaining gap in my table. I want to show you that for the basic fickle variables different from t, the corresponding components of d are all greater than or equal to 0. So let's prove this below. In this case, I is fickle. So since I is fickle, we have xi equal to 0. Thus, the ratio that we consider when we choose the variable that exits the basis is equal to 0, because this is the ratio minus xi divided by di, and since xi is 0, this ratio is equal to 0. So now let's prove that di is greater than or equal to 0 by contradiction. If we had di strictly negative, then the index I would have been considered when choosing the exiting variable, and it also would have achieved the smallest possible ratio because the ratio is 0. So now it would have been tied with other variables to exit the basis. So our pivoting rule comes into play, and Blend's rule tells us that the smallest index should exit the basis. But the index I, since it is fickle, it is smaller than t. Therefore, our pivoting rule shouldn't have picked t to exit the basis, but it should have picked I instead. So this is a contradiction. Let me write it down. So then, the pivot rule would have chosen I to exit the basis, since I is strictly smaller than t. And this is a contradiction, so we've shown that di is greater than or equal to 0. Now we're done with this specific change of basis. So let's consider the next change of basis, which is when t enters the basis. So there exists a basis, let's say b hat in the cycle, such that t is not in b hat and t enters the next basis. Now let C hat denote the reduced costs corresponding to B hat. What I want to do now is to go back to my table and consider a new column corresponding to C hat. Since t enters the basis, we know that its component t is strictly negative. For the variables I in B that are not fickle, we know that they're also in B hat, therefore the reduced cost is 0. Then for the last row, I don't care, so I'm just going to put a question mark. Now I have only 2 blanks in the table to fill in, and I'm going to show to you that they both are greater than or equal to 0. So let's show it below. I'm going to consider an index I different from t and fickle. So I will prove in one shot both these cases. Let's consider separately 2 cases. First, the easy one. If I is in b hat, then obviously c at I equal to 0. So we're done. So assume now I not in B hat. We prove it by contradiction. So if we had C hat I strictly smaller than 0, then my pivoting rule would have chosen I to enter the basis, because in this iteration we have that T enters the basis, but since I also has a negative reduced cost and is a smaller index than T, then the pivoting rule should have chosen I instead. So then the pivot rule would have chosen I, to enter the basis, since I is smaller than T. So we found a contradiction, thus C hat I is greater than or equal to 0, as we wanted to show. Next, I want to define a new vector. Define C tilde, which is equal to C hat minus C bar. And correspondingly, I will add a column to my table, C tilde. And at this point, I can understand few things about C tilde by just looking at the columns corresponding to C bar and C hat. Now in the first row, for the index t, we have that C hat is negative and C bar is 0, so their difference is negative. In the second row, for the index s, we have that C hat is greater than or equal to 0 and C bar is negative, therefore their difference is strictly larger than 0. For the next row in my table, I have that C hat is greater than or equal to 0 and C bar is equal to 0, therefore the difference is greater than or equal to 0. In the next case, they're both equal to 0, so the difference is again equal to 0. And finally, in the last row, I don't know, but it doesn't matter. So I'm gonna put a question mark. Next, using the values in the table, we show that C tilde transpose D is strictly greater than 0. How are we going to do this? Well, we simply divide this inner product in its components according to the components in the table. C tilde transpose D equal to, so we have the component corresponding to T, then the component corresponding to S, then we have the sum of C tilde I di overall I in B, I different from T, I fickle. Then we have the sum of C tilde I di now for I in B, I not fickle. And finally we have the sum for I not in B and I different from S of C tilde I di. So now let's get back to our table and analyze all these products. Everything we need to do is to look at the columns corresponding to C tilde and D and multiply the corresponding entries. For the index t, we have strictly smaller than 0 times strictly smaller than 0, and the result will be strictly positive. For the index s, we have 1 times something strictly positive, and so the result is strictly positive. In the next row, we have greater than or equal to 0 times greater than or equal to 0, so the result is greater than or equal to 0. In the next row, we have 0 times something, so it's equal to 0. And similarly, in the last row, we have 0 times something, and the result will be equal to 0. So in our sum, all the elements we're summing here are greater than or equal to 0, and at least 2 of them are strictly positive. Therefore, the sum is strictly positive. If you remember, our proof is by contradiction. So now, to obtain a contradiction, we show C tilde transpose D equal to 0, which contradicts what we have just shown. How are we going to obtain that? Well, let's write C bar transpose using the definition of our reduced costs. And this is C transpose minus C B transpose B inverse A. And let's write also C hat transpose using our definition of reduced costs. This is again C transpose minus C, now B hat transpose B hat inverse A. This implies that C tilde transpose is equal to, so in the difference between C hat and C bar, the C vector cancels out, and then in the remaining part of the formula I can factor out A, which is in common in the two expressions, so I obtain that this is equal to C B transpose B inverse minus C B hat transpose B hat inverse times A. But now if we multiply on the right by D, we obtain 0 because we've shown long time ago that A times D is equal to 0. So AD equal to 0 implies C tilde transposed D equal to 0. So we have a contradiction. And this concludes the proof that Blend's rule avoids cycling. And this also concludes our lecture on anticycling.